I see we are close to 60 participants, so I think we can start the session. Good morning. My name is Costas Vournas from National Technical University of Athens in Greece. I'll be chairing this session, which only has one survey paper, together with my friend and colleague Thierry van Cutsem from the University of Liège. And as you see, this is a multi-part, multi-author paper, which touches on the fundamentals of power system modeling in the presence of converter interfaced generation. The fundamental question that we would like to set, not necessarily answer, is whether the fundamental frequency constant frequency representation that is typical of the phasors we're using in power systems is a good enough approximation to study modern power systems, and more than that, power systems in the future, where they will no longer be dominated by large synchronous generators, but rather on converter interface generation. And this is not necessarily, or not only in the framework of the microgrid, but rather we are thinking about large power systems. So there will be 4 presenters, because, as I said, this is a multi-subject paper, and the presenters will be introduced by my co-chair, Thierry. But apart from the presenters and the 2 chairs, there are also 3 other authors that I'd like to mention. Trevor Gaunt from the University of Cape Town, Vijay Vittal from Arizona State University, where they are around midnight now, and Marco Liserre from the University of Kiel in Germany. And all authors, not only presenters, will be available in case there are questions to be asked. Apart from the sections of the paper that will be presented today, there are several examples that are detailed in the paper, so maybe some of the questions can be directed to them. So the main topics to be discussed is, as I said, the adequacy of Phasor and how we can generalize this to signal processing techniques, the classification of converter controls, and also the effect of the modern structure of the power system to protection and control. So with this, I'd like to switch to my co-chair, Thierry, to introduce the first speaker.
Good morning, everyone. This is Thierry van Cutsem speaking from the University of Liège, Belgium. So I will immediately introduce our first speaker, Mario Paolone. Mario received a master and a PhD degrees in electrical engineering from University of Bologna, Italy in 1998 and 2002. In 2005, he was an assistant professor in power systems with the University of Bologna, where he was with the Power System Laboratory until 2011. Since 2011, Mario has been with the Swiss Federal Institute of Technology in Lausanne, Switzerland, where he is currently a full professor and the chair of the Distributed Electrical Systems Laboratory. Mario, the floor is yours.
Thank you very much, Thierry, for the kind introduction. So let me jump into the context since there is a lot of material to to present, and the context refers to a specific section of the paper that has been written by Thierry that is showing and discussing real-life issues that we have experienced so far. But before going into this part of the presentation, let's recall that power systems are large, nonlinear, multi-scale, discrete, and continuous complex systems that have been successfully engineered thanks to the fact that we were always relying on white box models and parametric models, relying on specific assumptions. So one of those that was mentioned by Costas is related to the study of dynamics of electromagnetic transients. And essentially, the main hypothesis that we do here is that the response of the system is dominated by the one of the synchronous machines. And this simple hypothesis is enabling the use of time-varying phasors that are enabling all the possible writing of problems ranging from short-circuit analysis to optimal power flows and so on and so forth. When this hypothesis is violated, typically what we do is to move into electromagnetic transient studies where a more detailed set of differential equations are used to solve the system, and we relax the hypothesis of time-varying phasors. However, the increased penetration of converted interface generation and HVDC, we don't have to forget that there is also this other component to the system, is challenging this above the composition of power system studies. And there might be a gray zone that we have to discuss and pay more attention to. So there are new needs in dynamics, control, and stability studies of systems characterized by these boundary conditions. Now, let's go into the real-life examples that I was mentioning before. And I start with an event that many of you are familiar with, which is the blackout in South Australia of September 28, 2016. So this is the sequence of the events. So there are multiple tornadoes in South Australia that were tripping multiple high voltage transmission line circuits that were resulting into faults in a very quick succession. So these faults were generating voltage dips that were triggering several wind farms that were running back about 0.5 gigawatt of power. So this compression into the wind farm output was compensated by an increase of the power imported in the South Australia region from Victoria. However, this increase of the imported power was stripping the interconnection, and the loss of power and the loss of the import from Victoria resulted into a frequency that was falling so fast that load shedding was simply unable to recover the frequency, let's say the power balance, and then the frequency collapsed. What was learned from this event was a rate of change of frequency, what we call ROC-off, of pretty high value. So it is reported here for a specific time window of the event, and the measurement was an average of 6.25 Hertz per second, which is a pretty extreme value that is challenging phasor approximations, as we'll see in a moment. The second event that I would like to illustrate, in the paper there are 3 events that are detailed, as I was saying before, but let's focus on this one, is an event of August 16, 2016 in California, where a fault in high voltage was triggering a trip of more than 1 gigawatt of power fed into the system by PV panels and PV converters. And what is interesting to observe in this event is that the majority of the inverters was tripping instantaneously based on the frequency measurement obtained from their PLL. And it was determined that there was an erroneous tripping due to frequency changes in this converter. It was responsible of about 700 megawatt of loss of generation. There was also another issue related to some other converters that were tripping due to voltage variations that were beyond or above a window of 0.1 per unit around the nominal value. And these inverters that were somehow reducing their output were coming back into a pre-disturbance power injection at a very slow ramp rate. And this was essentially responsible of more than 400 megawatt of lost generation after the fault. So from these 2 events, we can summarize 3 main challenges that we may pay attention to. The first one is related to the adequacy of phasor approximation when we are in the presence of very high electromechanical dynamics, like the ROC-off that I was mentioning before. The second one is related to the control law of converter interface generation, how they have to be classified and improved, especially with respect to grid codes. And the third element is how to improve the performance of protection systems because they may misoperate, as we have seen in these events that have been just discussed. Now, let's start from this first point. And I would like to start from a first year engineering exercise, where I'm essentially computing the spectrum, the Fourier spectrum of two signals. The one on the left is a signal characterized by a single tone, a single component, let's say a 50 or 60 hertz component, corrupted by a tiny amount of noise. And what you see is that the energy of the spectrum is essentially concentrated in what we call a narrow band signal, essentially around a finite, in this case, a single component of the spectrum. Instead, if you do a Fourier analysis of a signal experiencing a rock-off like the one in South Australia with a negative ramp rate of 6 or 25 hertz per second, you see something interesting. You see that the spectrum is no longer narrow in the sense that it's pretty continuous and spread over a relatively big frequency range. Now, if you look at the typical frequency interval where we are studying power systems, this is a power system at 50 hertz rated frequency, and we study the energy of the spectrum concentrated between 48 to 52 hertz, well, you realize that only 32% of the energy of that signal is concentrated on that band. Then you may ask yourself whether a Phasor approximation is good enough to represent this kind of phenomena. Then what is natural to introduce is a definition of what we call narrow or broadband signals. So narrow band signals, for those of you who are not familiar with this concept, are signals with a discrete spectrum with an energy concentrated around a single or a finite set of sinusoidal components. Broadband signals instead are signals with a continuous spectrum of a generic bandwidth a priori, that you don't know a priori, where the spectrum of the signal and of course its energy cannot be reconstructed by a finite set of sinusoidal components. And this has a very important consequence when you're using a Fourier analysis, and in particular a discrete Fourier analysis. Now, when we are dealing with the concept of Phasor and we are implementing a Phasor reconstruction into any device, in any control or protection or sensing device, what you're essentially doing is that you're applying a discrete Fourier transformation over a generic signal x of t to reconstruct your Phasor. Now, the question is why this approach may fail when you have a continuous spectrum signal. Well, when we are analyzing with a DFT narrowband signal, essentially what we are doing is that we are projecting your narrowband signal over a kernel of the DFT, which is composed by a finite set of sinusoids, that is essentially enough to reconstruct the discrete nature of the spectrum of your signal. Instead, if you have a broadband signal, the fact that the spectrum is continuous is essentially violating the possibility or making the DFT analysis impossible to reconstruct the spectral content simply because the spectral content is continuous. Now, let's try to analyze which are the consequences of this simple approximation. And then to do that, let's consider this pretty simple system. So we have a two-node system. On the left, you have a generator that is a voltage generator with a generic time dependence voltage, where you can reproduce ramps of frequency, modulations of amplitude, phase, whatever you want. You have a transmission line of 100 kilometers. I forget to mention that the voltage generator has a face-to-face voltage of 380 kilovolts. So we have a 100-kilometer line with a frequency-dependent model. Everything is modeled into a time domain simulator. In this case, is the MTPRV. And then the transmission line is feeding a constant impedance load, let's say a constant time domain parameter model of the load that at 50 hertz and 380 kilovolts is absorbing 400 megawatt with a lagging cos phi of 0.9. What we wanted to do is to reconstruct the power that is transmitted by this system to the load, where the supplying voltage is experiencing, for instance, a frequency ramp with a rock-off of minus 5 hertz per second, or an amplitude modulation of 10% in depth at 5 hertz modulating frequency. Now, to do this study, we do something relatively easy and reproducible. So since we know the ground truth, we can compute the true instantaneous power which is the point 1 of the algorithm. Then for all the 3 voltages and currents, which are injected and absorbed by the generator and absorbed by the load, what we essentially do is that we add a tiny amount of noise, in this case 80 dB of SNR. And then what we do is what any control and protection system would do. Essentially, we are applying a handing window over a sliding window of 200 milliseconds. Forget to say that we are inspired here by the IEC standard 61000. So we are obtaining a spectrum that is windowed by the handing window. And then in order to reconstruct the most likelihood phasor, we are using a pretty standard technique, which is the interpolated DFT, which is used by several industrial grade devices to estimate the most likelihood phasor that is inside of the observation window. And then what we do is that we are back reconstructing your time domain signal using the estimated phasor. And then you are back reconstructing the power associated to these 2 phasors that we have estimated. And this is allowing us to estimate the error between the ground truth power and what the phasor has estimated. Now, if we apply this simple algorithm to our 2-bus model, where there is a frequency ramp of -5 Hertz per second, what you end up is to have an error in the 3-phase power, which is about 12 megawatts over 500, which are transmitted. If you do the same exercise, when the VA is experiencing a frequency modulation of 5 Hertz per second with a 10% of amplitude depth, well, here the error is way bigger. We are talking about 200 megawatt with spikes that are going above 300 megawatt, which is a pretty substantial error, as you can see. Now, to overcome these limitations of traditional phasor analysis and DFT, there are 2 approaches that have been discussed in the literature. So the first one is the use of dynamic phasors. So as you may know, this is something that has been largely used by the community of power electronic people. Essentially, you are extending the concept of phasor by embedding fundamental parameters time derivatives in your signal model. However, the problem of dynamic phasors is that they are still relying on a concept of a phasor that embeds the concept of DFT. So therefore, they might face similar model inconsistencies as those that we have seen so far. The other approach is relying on non-DFT based analysis, and I would like to give you a little bit more hints on this second one, which is pretty much interesting from the scientific and technical point of view. Now, let's recall a very simple concept. I mean, what is a DFT doing? Well, essentially, is taking your signal and is projecting it over a base of sinusoids that you have predetermined, which are composing what we call DFT kernel. Now, what if you're projecting your genetic signal over a functional base which is not based on sinusoids and is able to reconstruct the whole continuous spectrum of your system? Is it possible to do something like that? Well, the reply is yes. And this is what the signal processing community has called compressive sensing or compressive sensing techniques. Now, in order to leverage this kind of generic functional basis projection, we have to combine them with the usage of the Hilbert transform, simply because the Hilbert transform has a pretty interesting property. So first of all, let's recall what is the Hilbert transform of a generic signal x tilde of t. So the h of x of t is defined as 1 over pi times p times the integral from -infinity to infinity of x of tau divided by t minus tau, where p is the Cauchy principal value. We need the Cauchy principal value simply because we need to assign a value to the integral since its denominator is becoming null for t equal to tau. Now, the interesting feature of the Hilbert transform is that it allows us you to define what we call analytic signal, the x hat of t, which is composed by the original signal plus j, the transform, the Hilbert transform of your signal. And the feature of the analytic signal is that if you perform a Fourier analysis of the analytic signal, it does not have the negative frequency spectrum. Now, the fact that it doesn't have the negative frequency spectrum has several advantages, and one of those I'm going to recall in a moment. Now, let's try to apply the Hilbert transform and the analytic signal concept to our frequency ramp signal. So the x of t that you see here. So a cosinus of 2 pi f0 t plus phi 0 plus r pi t squared, where r is the ramp rate. So if you do the frequency, the Fourier transform of the signal, you end up into these two components that are embedding the continuous spectrum that I was mentioning before. You see this f minus f0 squared is essentially spreading the energy of your signal over the whole spectrum. Instead, if you're doing the Hilbert transform of this signal, you end up into a model that has a very simple parametric representation where the only parameters that you need to estimate are A, the amplitude, F0, phi 0, and the ramp, which are essentially the parameters which are characterizing your frequency ramp. So you see that you have a more compact and exact reconstruction of the signal using this Hilbert transform combined with the analytic signal representation. In the paper, there are several examples of how to derive these analytic signals for other type of signals, embedding modulations or steps or other kind of disturbances that it may embed into the fundamental frequency component. Now, the main idea of compressive sensing and in general their combination with the Hilbert transform is to build what we call a basis of a functional analysis, where essentially you build a dictionary, and this dictionary is embedding what we call atoms, and each atom is essentially responsible of representing a specific dynamic of a signal. Now, in power systems, we don't have so many dynamics that can take place into our signals. Essentially, we have frequency and frequency ramps. We can have amplitude and phase modulations, and we can have steps. And of course, a spectrum composed by the fundamental component and the harmonic component. So we don't have so many components to embed into our dictionary. Now, let's try to see whether we can successfully reconstruct our signal and our power transfer using the Hilbert transform and the functional basis analysis. So we do exactly the same exercise we did before with a true bus system. So we can compute the true power transfer of over the transmission line. So we have our three signals associated to voltages and currents. We are adding noise, and in this case, we are reconstructing we are computing our analytic signal thanks to the Hilbert transform. Then what we are doing is that we are projecting our analytic signal, let's say our analytic signal over our dictionary, which is the Hugger, that is essentially embedding inside all the possible dynamics, as I said, frequency ramps, amplitude and phase modulations, steps, and so on and so forth. And then what we have is that we pretend to have an algorithm which is identifying the minimum set of elements on your dictionary that are capable to best reconstruct your signal dynamics. And then what we do is that we are back reconstructing the power that our signals are transferring over the transmission line, thanks to this functional analysis that I was mentioning before. And then we are making a comparison between the reconstructed power, thanks to these analytical signals, and the one of the ground truth that we have computed at step number 1. So here I'm just showing the case of the frequency ramp applied to the tube bus system that I was showing you before. And you can see that we have a pretty much exact reconstruction of the power flow through the transmission line compared to a standard Phasor reconstruction technique. In the paper, there are many other examples related to other dynamics like amplitude modulations and the same application to a way more complex system composed by the IEEE 39 bus. And I invite you to read this part of the paper to have more insight on this analysis. I leave now the floor to my colleague and friend Antonello Monti, and perhaps I give the floor back to Thierry that is going to introduce Antonello.
Yeah, thanks, Mario. I'd like to take this opportunity to remind the audience to ask a question through the Q&A menu of the Zoom platform. So you can type your question and then we will proceed at the end with the questions, and there will be answers to specific or general question at the end. So now let me introduce the next speaker, Antonello Monti.
Mario, could you continue with the slides because I have a little issue with the operating system. Can you keep your slides on and I just click on it? Thanks.
No problem.
All right.
The operating system gave me trouble at the last minute. Thank you.
This is
So,
N-1 security. So Anto received his PhD in electrical engineering from Politecnico di Milano in 1994. He started his career in Ansaldo Industria, and then he moved to academia, joining Politecnico di Milano in 1995 and the University of South California, USA in 2000. Since 2008, he is the director of the Institute for Automation of Complex Power System within the Ion Energy Research Center at RWTH Aachen University. And Dr. Monti has been the recipient of the 2017 IEEE Innovation in Society in Societal Infrastructure Medal Award. So Anto, the floor is yours.
thank you, Thierry, for the kind introduction. Thank Mario to prepare the terrain for my talk, for my part of the talk. So similar to the analysis done in the signal process, we'll address the same question from a simulation perspective. So how can we develop this, as Mario said, gray zone between an electromagnetic type of simulation, the classical EMT and the classical phasor analysis, and then how do we bring the same philosophy of the Hilbert transform in the simulation environment. The idea is, or the proposal at least, is to use a frequency shift to the original signal, so working with an analytical signal that at the end, from the simulation purpose, can be interpreted as the Hilbert transform. The nice thing of this approach, and performing simply in this frequency shift, is that the derivative operator can be formally defined, and then a classical extension of the modeling from the EMT is rather feasible. Next slide, please. So what we see here is that we have the signal we would like to study is represented by an analytical signal, the capital X, multiplied by a frequency shift operator. So what the idea is that the original spread, if we would do it with an EMT analysis, would require a quite short time step. So the computational perspective would be really heavy. Vice versa, if we perform a frequency shift first, then the system frequency content, which is the triangle, will move to 0. And with a smaller time step, we will be able to cover a wider range of frequency. Here is an interesting problem because at the end, the question is a compromise of computational complexity, because on one hand, the analytical signal will require more variable to be solved. On the other hand, we require, depending on how wide is the spectrum, and possibility of increasing our time step. Once the simulation, the other challenge is once we have multiple bins and how you slice in a different perspective, and that was also Mario previously introduced. Here there are different options and that are possible. If they are coming directly from a power electronic system, people will think to build several bins in a way similar to a Fourier analysis. So using the Fourier as an indicator how to define the bins that we want to have. But at the end, this will bring to a multiple frequency shift that will bring then to a higher computational complexity. And that's what you see here, that moving the one frequency bin, then clicking again, it will move this will, with a single one will not work. And then clicking again, you shift and you find a compromise. At the end, after the definition of the shift operator may be inspired by Fourier, but also by a combination of Hilbert and Huang transform. This has been analyzed in several publications. The main limitation of the Huang is that we require pre-processing to define those bins, or we define, as Mario also anticipated, the possibility of a standard way to do it so that you get the best of the world. Once the calculations are done, you shift back the frequency and you can back to a quite detailed resolution of your signal, like in an EMT type of study. What you see here is an analysis of how the simulation time step play a role as function of the shifting frequency. And obviously, the more we center the original shifting frequency to the key frequency of the signal, which typically will be the 50 Hertz, the better it is. But in general, we have a significant improvement with respect to performing the simulation in a classical EMT analysis, and we get significant reduction in the computational performance. And here you see a comparison between performing an EMT analysis with different time step or performing the same with this analytical signal shifting frequency, even when we have a significant error in the frequency of the main beam, let's say. Here, what we are doing is shifting at 50 Hertz, but actually we are simulating a system running at 60. So there is a significant error to begin with in the shifting frequency, but still with a time step of 10 milliseconds, we get a very good accuracy of the signal, which is absolutely impossible in the EMT. And that shows how this game of widening the spectrum in relation to the time step can be done. Next slide. As said, then the key point is from there you can build a concept of solver. Actually, my group, we built this as an open source solver that people can access and increase the content of library. We decided to go for a nodal analysis approach for the system level solution. And at the end, what is nice in the model that you get something very similar to what in EMT will be a resistive companion approach, but the derivative adding two terms show this capability of the model in a smooth way to move from a Phasor analysis to an EMT analysis just as a function of the time step, but without the need to change your model whenever you want to change the level of details, or better, how bright you want your beam of frequency to be. Next slide. We've been studying that from a scalability perspective. What we have been showing here is how you parallelize the solution and what you can do on very large systems, and exploring different solutions of parallelization from transmission line modeling or dioptics as a way to parallelize section. The key point is that the network solution matrix is still the key element of cost from the calculation perspective, but you see that with increasing the number of thresholds in the multi-kernel processor, you get a significant improvement. And we were able to run network here with 700 nodes, even in real time on standard computer, which is quite impressive compared to going for a commercial solution for a real-time simulation. Next. Yeah, that completes my part. Thank you, Mario, for being the director, and sorry for my operating system giving me trouble.
No problem.
Thank you very much, Anto. And now we move to the next topic of this survey, and is going to be presented by Xavier Guillaud. Xavier received his PhD from University of Lille in '92, and he joined the Laboratory of Electrical Power and Polytronics in '93. He has been professor in École Centrale of Lille since 2002. First, he worked on modeling and control of polytronic systems. Then he studied integration of distributed generation and especially renewable energy in the power systems. Nowadays, he's more focused on the integration of high voltage power electronic converters in the transmission system. He's leading the development of a laboratory, including power electronic converters interacting with virtual real-time simulated grids. Xavier is involved in several projects about power electronics in the grid within the European projects, or a number of French electrical utility projects. So Xavier, it's your turn.
Thank you, Thierry, for this introduction. So before starting the discussion on the various types of control, I recall that there are two types of converters which are connected to the grid. First, there are some converters which are called two-level or three-level voltage source converter, which are going from 100 watts to 10 gigawatts for mainly renewable application. And on the other side, we have the MMC voltage source converter for the HVDC application up to 1 gigawatt. Since we are not interested in the internal behavior of the converters, all the converters are simulated here to a simple two-level VSC. So the main role of a voltage source converter is to generate a state of three-phase modulated voltage, VMA-VC, from a DC bus voltage. We are using a classical modeling of the converter, and we suppose that there is a set of three-phase reference signals in the control, VMA-VC reference, such that there is an equality between these references and the average value of the modulated voltage. With this assumption, it is possible to assimilate the VSC to a very simple voltage source, which can be driven by the control. Since we are focusing on high voltage connection, the resistance will always be neglected. Currently, we can say that nearly all the power electronic converters are driven by a grid following control. Due to the increase of the power electronic converters in the power system, the question of introducing grid forming control in the converter is asked. But what is the real difference between the grid following and the grid forming control? An intuitive answer could be to say, on one side we have current injector, power injector, on the other side we have a voltage source for grid forming. That's true, but it's not enough. A grid forming converter has also to control its own power, which is exchanged between DC and the AC grid. So we cannot say only that one is just a current injector and the other is a voltage source. We don't have to forget that the first priority of the power converter is to exchange active power. Of course, due to the recall, they also are asked to provide some ancillary services such as voltage, which is about frequency regulation. But the control of the active power is a key point in the control of the VSC. Let's see two different solutions to do that. Before analyzing the active power control, let's present first the very simple model we are using. It is composed of two voltage sources. Vm represents the phasor of the voltage which is modulated by the converter. Vj is the phasor of the voltage at the point of common coupling. X is the connection reactance. From this model, we can deduce the very well-known expression for the active power. P equal to Vj, Vm over X since psi. Based on the expression, how can we control the active power? Obviously, it's not possible to have a direct control of Vj. We all know that the RMS value of Vm has a stronger influence on the reactive power. So the only solution to control the power is to control the power thanks to the angle psi. This is the origin of the grid forming control. It means that the active power control has to generate a reference for psi. In fact, since we are only controlling the modulated voltage, it's only the modulated voltage angle which is driven by the converter. So the control is slightly modified. It has to generate the phasor modulated voltage angle, which is called here delta L. We have introduced the control with the phasor angle, but of course, in the real life, the control is operating with time domain angles. Then the control has to be modified, and as it can be seen on the figure, to generate the time domain angle, which is called here theta. The second solution to control the active power is built on the very well-known current formulation, power P equal to Vgi cosinus phi. If we want to control the power, we have to control the current in phase and magnitude. This is the well-known principle of the grid feeding, grid following control. In the literature, the terms feeding and following are equivalent. So from now, we will only use the term following. Then we can deduce that the output of the power control is a reference for the active current. Since the voltage is a voltage source, the converter is a voltage source, we need a current control. Of course, the same kind of rule is implemented for the real power or the voltage. Let's see now the influence of the choice of the active power control on the way to synchronize the BSC to the grid. Let's start with a grid forming control. We recall the very basic power. If this loop is stable, then psi is constant. Then the difference between theta m and theta g is constant. I recall that theta g is the grid angle. Theta m is a voltage angle modulated by the VSC. If this difference is constant, then in steady state, it means that the VSC is synchronized to the AC grid. An external synchronization, as a PLL, is not compulsory. Obviously, there is no inherent link between the power control and the way to synchronize the AC grid in the grid following control. This is the reason why a dedicated synchronization algorithm is compulsory in this case. So, to conclude this point, first difference, the major difference, which is induced by the way to control the active power, is the synchronization principle. The grid following controller needs a PLL. This is compulsory. The grid forming controller is not compulsory, but it doesn't mean that the PLL cannot be used in a grid forming control. Just say that it's not compulsory. Sometimes it can be very helpful. We will see that further. Let's see now the influence of the choice of the active power controller on the way to generate an inertial response. The fundamental principle of the inertial effect is a link between a power variation and the derivative of speed, meaning the second derivative of the angle. If it is possible to create a link between the active power and the second derivative of the angle, thanks to the control, an inertial effect will be created. Let's apply this idea to the grid forming control. Let's suppose that the power control is now composed of two integrators in series. We can see that the same kind of equation as for the real inertial effect appears between the modulated angle theta and the difference of power delta p. Of a closed-loop system with only a double integrator is a perfect oscillator. Of course, this system has to be damped. As you can see here, we add this damping effect, and this is the basic of the principle of the virtual synchronous machine scheme. Hence, with this type of control, it is possible to have an inertial effect without any frequency measurements. Again, this is due to the specific way to control the active power with a voltage angle. It is possible to choose a wide range of value for H. It's just a matter of control. With the grid following control, it's not possible to have this inherent inertial effect. The only solution is to derive the grid frequency and integrate this derivative action in the power reference. It's possible to implement this inertial effect with the grid following control, but it is much less effective than with the grid forming control due to the frequency measurement and the frequency derivation. Now let's see how to implement a grid forming control. The aim of the control is to generate a set of reference for the modulated voltage VA, ABC. The grid forming control generates the angle theta. The magnitude of the voltage is chosen with a DQ command and applied on an inverse part transformation to generate the voltage of the ABC reference. Due to the very small R over X ratio in transmission system, the poles of the grids are not very well damped. So the reason why we have to add a damping resistance during the transients. This is extremely important in transmission application. Since the connection impedance to the grid is very small, around 0.15 per unit or less, closed loop control for the voltage is not compulsory to have a good voltage control of the BCC. A reactive control can be added if needed. In case of a two-level VSC, an LC filter is added between the VSC and the point of concrete current. Current and voltage loop has to be implemented. With this kind of system, the grid forming control generates the voltage angle reference for the voltage across the capacitor and not the voltage, modulated voltage anymore. A specific design of this control has to be achieved for that. In case of a grid fault now, the grid forming converter reacts instantaneously due to its voltage source behavior. However, it has to be protected against overcurrents. Now, it exists two solutions, either a limitation of the DQ reference here, or the integration of a virtual impedance in the definition of the voltage. A third solution is a combination between both solutions to take advantage of the benefits of each solution. Let's analyze briefly the role of the PLL in the VSM scheme. In this scheme, an estimate of the grid frequency is used. In steady state, this estimate of the grid frequency is equal to the grid frequency itself, and also omega n, which is the modulated voltage frequency, is equal to the grid frequency. Since in steady state delta p equal to 0, it can be deduced that in steady state, the active power is equal to reference. We have the choice to add an auto loop for a frequency loop control or not. If we don't have this PLL, the single difference, delta P, of course, is still equal to 0. Omega M is also equal to omega G. But omega G is not always equal to omega set. It results in a resolution between the active power and the grid frequency, which is exactly the same equation as a classical frequency group control characteristic. This is what we call that a kind of compulsory frequency support, which is not always wanted for any kind of sources. K has to be chosen with respect to some load sharing capability when the grid forming VSC is connected on a grid with different sources participating to the frequency support. Of course, it exists many other types of grid forming control. Circuit converter, which is very similar to VSM. Group control formulation, also very similar to VSM. Virtual oscillator, machine control, and maybe others. How to compare and classify the different types of control? Is it possible to define a set of key performance indicators for different grid controls in the case of transmission system application? Let's try to define these indicators. First point is about the active power response time, which is extremely important. Is there an inertial effect? If so, how to characterize this inertial effect? What kind of frequency support is provided? What is the dynamic of the voltage control? What about the robustness of the control with respect to the grid impedance at the VCC? Usually the grid forming control is quite robust, but it has to be checked and studied. How this grid forming control converter is protected against overcurrent, and also what about the resynchronization of the fault? This needs to implement a very simple benchmark to test all these properties. We have developed this kind of benchmark, and they are publicly available. You have some information in the paper about that. At the end, we can conclude that the classical grid forming controls, such as VSM, has already very good characteristics. With this solution, there is a close link with the traditional view of the power system dynamics, but with two major differences. H value can be modified even on the fly, and the active power management is much faster than in a traditional power source. Of course, more innovative control can be developed, but they should be defined clearly if they have better performances on the proposed question. Till now, there is no proof of evidence for high power applications. Let's conclude now with the integration, some words about the interaction among converter interface generation and power system stability. This figure records the different layers of control and their frequency operation. The control loops are properly designed so as to avoid unstable interaction among them. Yet, in the bulky power system with high penetration of power-based generation, new stability is challenged due to an interaction between converters and electrical grid may occur. The multiple timescale control system of power converter will impact on stability by close coupling with dynamic machine and other power converter. Small serial stability of power converters can introduce negative band damping in the power system, introducing a resonance in the wide frequency range from subsynchronous up to harmonics of several kilohertz. And the synchronization principle of power converters and the dynamic can substantially impact on voltage stability. Recently, the need for new converters control strategy allowing faster injection of reactive power during grid fault in order to better support voltage stability has been debated. National Grid, which is the UK TSO, is indeed about the virtual synchronous machine, which has been introduced previously. And as we have seen also, the control of computational PLL converter, a VSM react almost instantaneously to grid fault without the need of frequency measurements. Recently, study has shown that the negative effect of synchronization units often implemented by means of PLL on the small signal stability of grid-connected converter. The figures on the left-hand side of the slide summarize the result of a Monti analysis where the effect of the interaction among synchronization units of grid-following control converters operating nearby have been addressed. It has been demonstrated that not only the stability margin of a grid-following control converter is reduced when other converters of the same type operates in the proximity, but also that the magnitude of the interaction among synchronization units of grid-following control control converters are strongly accentuated by the decrease of the grid short-circuit ratio. On the contrary, the study performed has shown that the grid-forming control converter does not suffer from such drawback. Some results, grid-forming control converter is suitable for operation under weak grid condition. The figure on the right-hand side of the slide shows the result of a robust stability analysis by means of structure singular value performed.
Thank you, Xavier, for keeping up with the time. And now I'm going to introduce the last speaker. It doesn't really need some kind of introduction, but let's be fair. Sakis Meliopoulos graduated in electrical and mechanical engineering from the National Technical University of Athens in Greece in '72 and got his master in electrical engineering in '74 and a PhD degree in '76 from Georgia Institute of Technology in Atlanta. Sakis is presently the Georgia Power Distinguished Professor in the School of Electrical and Computer Engineering at Georgia Institute of Technology. He serves as the Site Director, Power System Engineering Research Center, Associate Director, Institute for Information Security and Privacy, and Sakis is the Academic Administrator of the Power System Certificate Program. Sakis' research area is very broad, but let's quote in particular protection, control, operation, and optimization of electric energy systems. So, Sakis, the floor is yours.
Good morning, everybody. Are we sharing the screen? Are you seeing my screen or?
You need to click on the green button at the bottom, share screen, and then you select your application.
Yeah, somehow I lost the
at the bottom of this
connection. Yeah. 1 second, I guess. I lost the Zoom connection. Can you hear me?
Yes, we can hear and see you perfectly. Just that you need to share the screen.
Okay, very good.
Thanks, by the way, for being with us at this time of the day.
Yes. Can you see my screen?
Not yet. You need to share screen, then you need to select your application. Okay, coming. Yeah, perfect.
Okay. Excellent. Good morning. It's real morning here in Atlanta, and I need to catch up with time-wise because we're running slow here. The first, I'm going to talk about two things, I guess. First of all, some of the work that is done at Arizona State University by Professor Vittal. This work has to do with controls and models for positive sequence stability studies. It is important to understand that most commercial positive sequence stability software packages use a time step that is pretty long, about a quarter cycle of either 60 or 50 hertz. As a result, models for converters have to be cognizant of this time scale. Also, the important thing is that these are studies for transient stability, and typically we neglect the fast electrical transients, and we represent the electric transients, we represent the electrical quantities with phasors. Now, traditionally, models of inverters in these simulations use a current injection model, and that generates a lot of problems, especially when we're dealing with weak systems. At Arizona State University, under the leadership of Professor Vittal, for the last few years, some models have been developed, which is they represent the inverters as controlled voltage sources. And you can see here on this slide, the basic principle. Basically, there are two inner control loops, one for controlling reactive power, and the other controlling real power. And the end result is to the left of the slide. You see a voltage source behind an impedance, and that is a control model by the controls. And it turns out that this model is quite robust. It does have the limitations of the current injection, and a lot of tests were done, especially under the a group at the Western Electric Coordination Council in the United States. This group is trying to develop models of inverters for various studies in the system. And under this program, there was a lot of evaluations of these models. And eventually, this model was adopted. I will present certain results here. First of all, a simple example from the IEEE test system. And the studies had to do with the fact that we can utilize detailed time domain simulation methods. And in this particular case, the Arizona State University folks, they use the Plex program to simulate detailed time electromagnetic transient analysis of this model and compare it to the new method, the new modeling of the inverters. In this particular case, the IEEE system that is shown here, the generator on bus 1 was replaced with the inverter interface generation. And in the next slide, you see the results of this simulation. And what you see here is 3 simulations superimposed. One is the Plex simulation, which is a detailed time domain simulation program. And this is the solid line. And this is basically the standard to which we compare the other analytical methods. And the positive sequence voltage source modeling shows that it has pretty good agreement with the Plex simulation, while the traditional positive sequence boundary current model, it provides totally different results. For example, in the initial simulation after the disturbance, you see a zoom-in view of the waveforms, and you can see clearly that the proposed control voltage source model pretty much matches relatively closely the Plex simulation, while the positive sequence boundary current, it is totally off and is different direction. Similarly, this is both for the active power output and also for the current output of the inverter. Now, the same model was simulated by replacing all the sources with converter interfaced sources. You can see this, the results here. And again, the proposed voltage controlled voltage source matches relatively well the Plex simulation, while the use of the current injection model gives totally different results, which are not shown in this slide. For more information, you can see here the certain references that you can consult for more details. And in addition, the present paper, I guess you can. There are more details in the. Now, the result of all of this work is that the WCC have adopted this model, which is basically a control voltage source of inverter generator, inverter interface generation. And of course, that includes also a PLL representation and so on. But on the other hand, it requires a time step that is shorter than the traditional quarter cycle, that is requires a 1 millisecond time step for good results. And the overall model that the WCC has adopted is shown in this slide. Yep. There is no time to discuss everything in detail. So I will move to the next topic, which is the effect of converter interface generation on protection. And of course, that generates new and the new challenges in protection are added to existing old challenges, because as you know, we do not have a protection system that is foolproof for all the types of faults that can be encountered in the system. We have what we call protection gaps. Now, for a long time, people have been warning that the inverter interface generation will generate misoperations in relays. And now we live in an era where we have seen these operations in actual systems for many, many years now. And as a matter of fact, Mario showed one particular case from the blackouts in California in the few years ago. So what causes that? Well, inverter fault currents are primarily determined by the inverter controls. And in protection, we need high fault currents to detect faults and so on. One approach there is to oversize the inverters, but of course that will have economic and practical limits. The duration of fault currents from converter interface generation are relatively short. And another important issue is that inverters do not generate substantial quantities of zero and negative sequence currents. And many protection systems depend on the existence of zero and negative sequence currents for the detection of the fault and appropriate action. Now, a lot of countries have approached this problem by simply requiring inverter manufacturers to modify the control so that during a fault, the inverters can provide negative and sometimes zero sequence currents to facilitate the operation of the protection. However, this is not a good approach. We're engineers. We really need to have better approaches to deal with this new problem. Another issue with converter interface generation is that frequent topology changes because that these systems come in and go more often than in a typical synchronous generation and so on. And of course, to all of these problems, we have to add the existing protection gaps we have in the electric power systems. Here is the event that I mentioned. Mario discussed this event. I would like you to focus here on the geographic extent. You see the symbol of fire in this graph where the faults occurred. And notice that where you see the sign of the sun, there are PV facilities there that were dropped out because of this fault. In reality, the fault was cleared successfully. As a matter of fact, the fault that caused this blackout was was cleared in 3 cycles. Therefore, normally this will not cause any problem, but because of the dip in frequency, which was very minor, about 120 millihertz, and also the clearing of the fault generated a phase shift in the voltage waveforms, and that confused the controls, if you like to use this naive term, I guess, of the PV facilities, and they dropped the facilities out. Now, this is very important event because as we have more and more converter interface generation, disturbances that normally do not cause any problem in the system will cause dropouts of these facilities, and these dropouts are associated with high levels of loss generation, and that can cause additional problems. Okay. Now, in the paper, we describe in another event, the event of October 9th, which was basically the same procedure. We lost generation because of the interaction of the controls and the protection of the inverters in the renewables. In this particular event, we lost about 900 megawatts. Now, the study of these cases provide useful information for better design of inverter controls, but also we have to realize that to deal with these problems, the inverter controls have to become much more complex, and complexity brings more problems. Okay. Now, to summarize, the penetration of converter interface generation in the power system generates a lot of new problems for the protection. And I have here listed a number of issues that we have, and we've seen, as I said, protection misoperations because of these characteristics of the inverters. So one thing I would like to show you here is that on the top slide, you see, on the top trace, you see a conventional fault in a system with the synchronous generators, and you see that the pre-fault current is relatively very small, and during fault we have a high fault current, we have a DC offset, and it's not shown in the slide, we have 0 and negative sequence components. The lower set of traces is the current following a fault at the system that has inverter interface generation. And you see that the currents are relatively small, the fault currents are relatively small, and if we analyze these waveforms, we do not have negative and 0 sequence components, which affects the operation of the system. So these different characteristics causes a problems. And the conclusion is that as we have more and more converter interface generation, we're going to have more and more problems with protection and control in the power system. At Georgia Tech, and of course, there is a lot of research to deal with these problems. You see here a list of various approaches: model-based adaptive relaying, distance impedance protection is utilized for power distribution systems with distributed generation, directional overcurrent, relays with adaptive settings, etc., etc. These approaches are good. On the other hand, they become very complex. And as I said, complexity brings a lot of additional problems. At Georgia Tech, we've been working in the past few years for a new approach in protection, which will alleviate most of these problems. And the idea of the new approach is very simple. Basically, it is inspired from the differential protection function. The differential protection function basically all it does, it looks at the device and protection device to be protected, and monitors the sum of the currents into the device. Utilizing the generalized Kirchhoff's current law, the currents have to be 0, and if they're not 0, then there is something internal problem in the device, and we trip the device. Now, the differential protection is one of the most secure protection functions we have in the power systems. On the other hand, does not cover all the possible faults that can happen in the power system. So we extended this idea and say, why don't we use the following thing? Why we don't use all the measurements we take in a protection zone, generator, a transformer, and so on, voltages, temperatures, speed, and so on, depending on what is the device, and then try to see if the measurements are consistent with the mathematical dynamic model of the device to be protected. And basically, we compare the measurements to the model, to the detailed dynamic model of the device to be protected. And the best way to do that is through dynamic state estimation. And the results of the dynamic state estimation tells us, yes, the measurements fit the mathematical model of the protection zone, or it does not, in which case it indicates an internal fault, an internal abnormality, and so on. Time is running out. The way this relay then operates is we have the merging units that are shown here, which are data acquisition systems. And of course, we need to have a mathematical model of the measurement that we've taken. And in addition, we can generate virtual pseudo and derived measurements based on the topology of the device we have. And then we have a number of measurements, and we run through the dynamic state estimation, which give us a plethora of information. Here is the user interface of the relay. A lot more possibilities now. And what I want to focus on is that the dynamic state estimation is computationally intensive. And what I'm showing here is that a particular operation of a protective relay of this sort. And notice that this dynamic state estimation is done every 416 microseconds in this case, because we're using sample values and so on, of course. And the computations, the analytics of the relay takes about 125 microseconds. So it can be done within the time frame that we have in order to do the analytics and go to the next set of data as they're streaming in into the relay. And of course, there are a lot of possibilities here. That is, we can do visualizations of, because the dynamic state estimation now has the information for the detailed information for the device. We can do visualizations of what's going on in the device and so on. So the sky is the limit in this area. Yeah. So I would like to conclude with a very simple example of and a comparison of distance protection to estimation-based protection. And here I have a microgrid that has PVs and a wind. I'm focusing on a fault which is on the circuit between buses I and double I, as it's shown in the microgrid picture. You see the actual circuit on the insert as well. The fault is in the middle of that circuit, and we're comparing the performance of the distance protection. The distance protection basically estimates an impedance, and if the impedance is within the characteristics of the relay, then it trips the circuit, otherwise it does not. Notice these are the characteristics of the protection zone, the distance relay. And in this particular case, the fault is seen outside the characteristics, even if it is in the middle of the circuit. So this is a misoperation of the relay because it's not going to see the fault. The result of this is the fact that we have a system with inverters, and we have a 5-wire system basically for the circuit, and that confuses the distance protection. Now, if we see the performance of the estimation-based, you see the actual waveforms on the of this particular relay. What it is, for example, we have the current here, which normally the current is very small. You see only a slight increase in one of the phases because the inverters limit the whole current. But on the other hand, if we look at the residuals of computed from the state estimation, they become very high during that fault, and the confidence level that expresses the probability that the model does not meet, does not match the measurements, drops to 0 during the fault condition, even if the currents change.
I guess we are running out of time.
And therefore, let's conclude here. This example illustrates that in the presence of inverters, legacy protection may misoperate, and we really need to have new approaches to deal with this problem. Dynamic state estimation-based approach does not, is not influenced by the limitations of the inverters. So finally, we'll come to the conclusions that is modelers of power system dynamics should pay attention when applying or not phasor approximation to study systems characterized by high penetration of converter interface generation. Benchmarks should be used in, to validate the models through detailed time domain simulations. And protection models obviously have to change because legacy protection will not address the protection needs of systems with high penetration of CIGs. And furthermore, studies are necessary in order to provide modelers with guidelines regarding the use of the phasor approximation versus other types of representation like analytical signals and detailed time domain models. Finally, it is recommended that power system operators pay attention when writing grid codes related to systems controls in the presence of high shares of CIG. We live in a new environment and we're dealing with new problems, and therefore we have to provide new solutions to this, to the new challenges. Thank you.
Thank you, Sakis. We are running out of time and we'll try to accommodate a few questions. So let's start with the first question received this morning from Patrick Pansiatici. And Mario, maybe you can quickly read the question and give some answer.
Yes, thank you, Thierry. So the question is, you can read it, it's very interesting. Thank you, Patrick, for the comment. I understand that you propose to build a dedicated dictionary of signals of power systems. Can you confirm? Yes, my group is working on engineering dictionaries for this kind of analysis. And then he's saying, but how can you build this? Well, the reply is pretty simple. There is a metric in compressed sensing that is called coherence between signals. So the coherence is defined as the ratio between cross-spectral densities of two signals divided by their auto-spectral densities. Essentially, it's a measurement of how much two signals are overlapping each other in the spectrum. Now, if you build a dictionary with atoms that are representative of typical dynamics of power system signals, and you minimize the coherence of the dictionary, you can build a dictionary once and forever. So the reply is yes, it's possible. And actually, there is a group of researchers in my lab that successfully build such a dictionary, and we hope to publish soon the results. Then Patrick is saying, what if we compare this with the standard wavelet or other kernels? Well, with standard wavelet, in particular, when we are referring to the discrete wavelet analysis, you have the problem that your daughter wavelet filters are covering a pretty large band of your spectrum. So you may incur in the same problems of the DFT. You may use wavelets in the continuous fashion, but computationally, this will be very, very tough because continuous wavelet analysis is very computationally expensive.
Thank you, Mario. We are running out of time, but still there is possible to extend a little bit this session. So I go with the next question, which is from Hui Zuo to Professor Guillaud. Can you comment on the advantage and disadvantage of implementing PLL in the grid forming control, considering the existing of broadband signals in the power system? What can be the approach to avoid the instability caused by PLL? Xavier, please.
Yes, it's well known that PLL is inducing instability, but it is in case of grid following control. If we use PLL in grid forming control, since the role of the PLL is not the same at all, we don't have this question of instability. We have done many studies of robustness of PLL with grid forming control, and it doesn't induce any kind of instability. In fact, as I explained rather quickly, I have shown that if you are using PLL in the grid forming control, we can decouple the inertial effect from the droop control effect. As I shown you very quickly, if we don't have this PLL, then we can have this, what I call a kind of compulsory frequency loop. And then it's can be a real drawback, because it means that all kind of sources could have to participate in the frequency regulation. It's not what we want. And if we have this information from the grid frequency, we can have this decoupling from inertial effect, which is good for the grid, and the frequency support. Well, I've done some other study where we can avoid this period, but I don't have enough time to explain that.
Okay, another question for Xavier from Rashid Sarkawi. From manufacturing point of view, is this new paradigm significantly will this significantly impact design and sizing of components and devices be connected to the grid, or appliances for that reason?
There are two parts in the answer. Either you have the MMC. The connection of the MMC to the grid is extremely simple due to the MMC topology. There is no filter. So it's just a matter of current limitation. But if we design the MMC for a given nominal power, then there is you design, of course, the current in the current limitation, and you will have, in fact, the same current limitation either for the grid following control or for the grid forming. So the design will be the same, in my opinion. On the VSC, we have a two-level VSCs. I shown you that we need a LC filter, and this LC filter maybe can be a little bit different, but not that much. So to sum up, I don't think there are a very large difference between both type of controls in terms of design of the converter.
Okay, thank you, Xavier. There are two questions that I will read, and I will ask either Antonello or Mario to reply. The first one is, one advantage of dynamic phasors is that they enable modeling the system as a linear time invariant one, which helps in small signal stability studies. Would the Hilbert transform offer any advantages when compared to dynamic phasors? And the other question is, since frequency is defined as a steady state term, is it still valid to use frequency domain analysis in the transient state? How do you consider the major reasons of different dynamics and so on? So Anto, would you like to go first?
Yeah, okay, I can maybe take the first part. Personally, we haven't done any small signal analysis starting from the modeling approach that we have. I think you can find a way to match, I mean, basically it's again, as Mario says several times, it's a question of gray zone. You can move from one domain to the other. So the frequency shift I introduced will bring to model that could be seen as time invariant. What would be the interpretation of this analysis would be maybe something to be discussed, and I haven't done studies on this already.
Yeah, perhaps I can complement also this reply regarding the use of the Hilbert transform. If you try to write the Kirchhoff laws in the Hilbert domain, you end up into a closed form transformation that allows you to write time domain expressions of Kirchhoff laws into the Hilbert domain, irrespective of the base that you're using for the Hilbert functional analysis. That's a very nice property, which is allowing you to solve, for instance, your circuit in the Hilbert domain and then come back into the time domain. That's a very known feature that you can leverage and write a solver, for instance, using the Hilbert instead of the Fourier transformation to project your signal from time domain to another domain. Regarding the question from Zhao Yuan, well, as I said, here it's quite improper to talk about frequency domain, because when you're dealing with the Hilbert transform, you are using what we call analytic signals. But yeah, the reply is yes, you can use this method to analyze transient into power systems with a bandwidth that is up to the modeler to be covered. And regarding your question on the dynamics, which was the cause of the dynamics, well, the reply is the converter-based generation, both the source and also the control, as it was also explained by Xavier.
Thank you, Mario and Anto. There are a couple of questions for Sakis. One question is from Taufik Korea. If power converters are able to limit correctly the current in case of balance and imbalance fault, why injecting negative and zero sequences when the activation of physical protection is not necessary? Sakis?
Yes. Well, thank you for the question. If I understand the question correctly, it refers to the country norms where they require negative and zero sequence injection by the inverters to facilitate the operation of the protection. Well, when you do this, the controls are, first of all, if we want to stick with the legacy protection functions, then it becomes necessary. And my point was that obviously when we modify the controls to generate negative and zero sequence currents, the controls become more complex. And my point is that we should look at different ways of doing the protection, not the legacy protection, such a way that we do not have to modify the controls to inject negative and zero sequence currents. That was my point.
Okay, Sakis, thank you. Now there is one last question from Keith Bell. I think it is addressed to the panel. Sakis said that these California events can help in the design of inverter controls. What does Xavier think those main lessons are, and have they been learned since those events in 2016? So I don't know who wants to answer first.
Yeah, I think Xavier should answer this question because basically what these events show is that whenever you have a combination of frequency transients and phase shifts in the voltages and the currents, that generates this issue. But I think Xavier has to answer the question in more detail, I guess.
I'm not sure I have the full answer to such a complex question, but I would say it's just a comment more than an answer. What we have seen is really that grid forming is much more robust than grid following control. So I think that it could help to have a more robust system. We have made plenty of studies in many applications, and so on. It's always more robust. I think that currently people are still fearing because there is no current control. In fact, it's possible to have this current control, I would say, on the fly, in fact. But in normal operation, it's true there is no current loop. Well, sometimes we can have this current loop. So I think that manufacturers maybe they are fearing that, how can I protect my converter if I have no current loop? It's just a matter of changing the mind about that. It's possible to have this current protection just when needed. And well, just I would say it's a general remark.
Okay, Xavier, thanks a lot. Thanks to all the presenters. I am sorry that we were not able to answer all the questions asked through Q&A, but we did our best. And now we are running into the next session, so we really have to stop it here. Thank you all for attending, more than 100 attendees. And thanks again to the presenters and panelists. Bye.
Thank you.
Bye-bye. Thank you.
Bye.
Bye-bye.